other is twice that other, and the sum of these is then twice the sum of those. So notice now that this result is pretty general, right? So I can take this point P and move it around the circle. Like say if I were to move the point P to P prime here, then I would have this circular angle, which is also half of this central angle, right? So, so angle, so this is going to be equal to twice angle QP prime S. You see that? So that these two angles are the same. How can I indicate? I have a little squiggly line, right? Those are the same angle. So independently, and you know, I could draw a line through the center and make the same argument, but I don't need to, right? I've already established that the central angle is twice the circular angle, and that's the general result. So part B, they say, now arrange points PQR around the circle so that O lies within PQR. Show why the same results here hold. Let Q prime be the point diametrically opposite Q on the circle so that angle PQR can be divided into two angles, and apply the case from part A above each of these smaller angles and complete the justification of this case. Right, so that's pretty much what I'm doing here. Well, they actually say move point Q instead of moving point P. So we know that actually point Q here has got to make a right angle. Why? Well, because QOR is a straight angle, right? Yeah, so this is 180 degrees. And so QPO must be a right angle, because you divide both sides by 2, you get angle QPO must be 90 degrees. So a triangle inscribed in a semicircle, which is, I think, the big takeaway from this as to the importance in Ptolemy's diagram, which is that if you inscribe a triangle in a semicircle, then it has to be a right triangle. And similarly, if you circumscribe a circle around a right triangle, then the hypotenuse will be the diameter of that circle. That circle. Okay. So that completes task 13. So in task 14, then we're going to apply that to Ptolemy's diagram. So let's do that. So in the opening letter of the last excerpt, Ptolemy proposes take the three right-angled triangles KEG, ZEG, and NEG out of the diagram, and in each case inscribe them within a circle. So what do we know? We know GK, we know GZ. How did GZ get to be 72? This is the extended bit of the excerpt, right? So here's the rest of therefore the circles about right triangles KEG, ZEG, and NEG. So let's do that first, okay? So we're going to take these right triangles and inscribe them in a circle. Okay. Where can I do this? So, what do we know about these? Yeah. So we got the angle KEG is 12, 8. 40, huh? So that's a pretty small angle. So KEG, it doesn't look that small here, right? Because this diagram is not to scale, right? It's just for the purposes of making nice, clean observations, right? But this angle looks to be significantly more than 12 degrees, right? However, let's draw it in the circle. So, so if we draw a proper right triangle, like so, where this angle here is 12 degrees, what is it? 8 minutes and 40 seconds. And so what's the circle going to look like? Now, it's going to be like that, right? Is that a round circle?
That's an open.
Yeah. So I could probably do this more readily using our software. So let's just move this off to the side. Take a circle and remove the circle. So then I want to draw a diameter of the circle. So I guess for that I'll say give me a ray like so, and tell me where that ray intersects the circle, and then hide the ray because I don't care about it anymore, and draw the diameter like so. Right? Okay, now I want to construct a 12 degree, so I want to rotate this line. What happened? It didn't give me the right tool. It does that, doesn't it? So rotate around a point. So I've chosen that. So I want to rotate this line around this point, okay? And how far? Well, 12 degrees, and I guess we need to convert 8 60ths of a degree plus 40 3600ths of a degree. And so how does this convert? Can we reduce by a factor of 4 here? So I get 2/15ths plus 1/90th. What is this as a decimal? Oh gosh. Well, 15 goes into 2. 1/10 of a time, and so that'll leave me a remainder of 5, and oh, that's too big. 300ths, so that's a repeating 3, and 1/9 is going to be, so this is going to be 0.13 repeating plus 0.01 repeating, is that right?
Mm-hmm.
So this is going to be equal to 0.14 repeating. And so I can just write 12.14. 1, 4. Is that, how many 4s do we need here? Is that enough?
That's enough.
Okay. All right. Oh, yeah, so it did, rotated to a point, but I wanted to, it's going to be shorter than the diameter, longer than the chord there. So I guess I need to get the point of intersection of this line segment with that circle, and then I'm going to hide the line segment and hide the point for that matter, and draw this segment here. Okay, and then draw this segment here, and we'll see what that the measure of this angle. Can I measure this angle? Let's see, how would I do this? Here, here, and here, and then if it's 90 degrees, it'll make the little 90-degree marker to indicate, yeah, that's a right angle. All right, so that's pretty convincing, and we know that this angle is, wrong side, huh? So how do we do this? Like this? Yeah, that's hard to see. About 12.14 degrees, right? I suppose I could measure instead this angle. 77.86 degrees, right? Okay, so what are we gonna do with that? Well, we also wanna do triangle ZEG, which is a 36-degree angle. So let's go ahead and, do we need a separate circle for that? I suppose we could make this one smaller, and then get another circle over here. And say, yeah, I want a radius line. So give me a ray extending from a point on the circle through the center, give me the point of intersection of those two things, and then hide this ray and draw the line segment instead. So like that. And then I want, whoops, don't want that. And I just want to sort of straighten that out, huh? So then, so I want to go 36 degrees, so I'm going to say take this angle, or sorry, rotate, right? Rotate around segments, so I'm going to say take this, and rotate it around here, 36 degrees, okay? And that'll give me